So imagine you're looking at a red stop sign,
All right.
and it is simply objectively red, right? Like that expectation of permanence is basically baked into how we navigate the physical world.
Yeah, absolutely. We rely on that.
Right. You don't expect that stop sign to just, I don't know, suddenly turn vibrant green just because a cloud rolled over the sun, or like because you walked past it with a flashlight.
Right, because color in our everyday experience is a fixed property. We categorize our entire environment based on that visual stability.
Exactly.
Yeah.
When you start looking at phenomenal gemstones, that baseline certainty just completely shatters.
It really does. We treat color as binary.
Yeah.
Like a sapphire absorbs certain wavelengths and transmits blue.
Yeah.
An emerald transmits green. And our brains just rely on that constancy.
Yeah, but then you find yourself looking at a visual landscape that acts more like a shapeshifter.
Oh, for sure.
So today's mission is to unpack the ultimate chameleon of the mineral world, a stone that essentially just breaks the rules of optical physics. I mean, we're talking about Alexandrite.
The absolute gold standard of color change gems.
Right. And to do this, we are pulling from a massive stack of source material. We've got comprehensive gemological reports from the GIA, the Gemological Institute of America, plus scientific analyses from American scientists and compound interest.
Some really heavy technical data in there.
Oh, super dense. But also, we're looking at 19th century Russian mining archives and some modern buyer's guides from high-end jewelers.
It's a really great mix of the hard science and the actual market reality.
Definitely. The goal here is to help you, the listener, understand the precise atomic mechanics behind its legendary color change. We want to get into the bizarre geological anomalies required to even create it, and how modern labs separate the natural wonders from all the synthetics out there.
Which is a huge issue in the market today.
Oh, massive. So, okay, let's unpack this. We have to start with the main event, right? The magic trick.
The Alexandrite effect. It is the cornerstone of this entire discussion, the defining characteristic of the stone.
People always use that one phrase, right? Emerald by day, ruby by night.
Yeah, that's the classic shorthand for it. But honestly, that phrase almost undersells the severity of the shift.
It really does. It sounds like a marketing slogan.
Exactly. But we are not talking about a gemstone just looking a little, I don't know, a little washed out in dim lighting. In natural daylight, or even under, standard fluorescent office lighting, a high-quality Alexandrite appears as this lush, vibrant green.
Like a pure emerald green.
Right. Or it might lean toward a bluish green or a teal.
Yeah.
But it is definitively green.
But then, and this is where it totally messes with your brain, you take that exact same stone, set in the exact same ring, and you walk into a room lit by incandescent light.
Like a traditional warm light bulb.
Right. Or candle flame. The green just vanishes entirely.
It's completely gone.
The stone undergoes this drastic transition to a purplish red, or like a rich raspberry, or a deep ruby red.
It literally looks as though someone physically swapped the gemstone out of the setting while you were walking through the doorway.
It's wild. So how is this actually happening? Like, it feels like magic.
Well, unpacking why that happens actually requires looking at the light sources themselves, rather than just the stone.
Oh, right. Because we always just assume light is light.
Exactly. We operate under this assumption that white light is just neutral and uniform, but in reality, light is a composite of various wavelengths across the visible electromagnetic spectrum.
Right, the whole rainbow.
Yeah, and the sunlight is not evenly distributed across that spectrum. It is heavily skewed toward the cool end.
Yeah.
So it contains a significantly higher proportion of blue and green wavelengths.
Okay, so sunlight is basically pumping out extra blue and green.
Correct. But incandescent light flips that entirely. The warm, flickering light of a candle or the glow of a tungsten filament in one of those old incandescent light bulbs that is heavily skewed toward the opposite end of the spectrum.
Toward the red and orange.
Right. Those sources emit massive amounts of red and orange wavelengths, but they are absolutely starved of blue and green.
So the stone is literally being bathed in a completely different set of energetic wavelengths, depending on which room you stand in.
Exactly. But what's fascinating here is where the physics of the stone meets human biology.
Oh, this is the part that blew my mind in the sources.
Yeah, because our eyes are not objective instruments. We aren't spectrometers. The human eye is a biological sensor, and it has uneven sensitivities.
Meaning we don't see all colors equally well.
Right. Under bright daylight conditions, which scientists call photopic vision, the cone cells in our retinas are highly active, and they are acutely sensitive to green light.
So we are naturally biased to see green when it's bright out.
Exactly. The human eye actually peaks in sensitivity right around the yellow-green part of the spectrum when there's plenty of light.
Wow. So our own biology is practically complicit in this optical illusion.
We are. And then when we move into dim, warm lighting like a candlelit room, our visual sensitivity shifts.
Because it's darker.
Yeah. As the overall light level drops, our pupils dilate, and the actual way our retinas process the available spectrum changes, we become relatively more sensitive to the red wavelengths that are dominating that candlelit room.
Okay, so wait. Does this mean the stone doesn't actually have a true color? Like, is it acting more like a mirror that just reflects the room's mood?
Oh,
Like wearing a mood ring, but driven by the light bulb instead of your body heat?
that's a fun analogy, but no, it's not quite a mood ring. What's fascinating here is that the stone is selectively filtering light, not just passively reflecting it. It's actively subtracting specific colors from the white light hitting it.
Okay, subtracting, so it's absorbing certain wavelengths and just straight up refusing to let them pass through.
Exactly. In daylight, it filters out the red light
Yeah.
and transmits the green and blue that the sun is pumping out so heavily. But in incandescent light, it filters out the green and transmits the red that the light bulb is providing.
So our brains and our eyeballs are basically amplifying the trick. We're biologically wired to perceive the green more intensely in the sun and the red more intensely in the dark.
Right. It creates this feedback loop between the mineral's chemistry and our own optic nerve.
That is just incredible. But this filtering trick is so unique, it raises a massive question. Like, what exactly is happening inside the stone at an atomic level to even allow this?
Right, because ordinary gemstones don't do this.
Yeah.
To understand it, we have to look at the mineralogy. Alexandrite is a rare variety of a mineral called chrysoberyl.
Chrysoberyl, which is beryllium aluminate.
That's right. And ordinary chrysoberyl is actually relatively common. It can be quite beautiful. Usually it's yellow or yellowish-green or brown.
But ordinary chrysoberyl does not change color.
No, it doesn't. The magic catalyst for the Alexandrite effect is a trace impurity, specifically the chromium 3+ ion.
Chromium. Which is wild because isn't chromium the exact same transition metal that gives rubies their red color?
Yes, it makes rubies red, and it's also the exact same element that makes emeralds green.
And in Alexandrite, it somehow manages to do both at the exact same time.
Exactly. So during the crystallization process, deep within the Earth's crust, trace amounts of chromium, and we're talking typically less than 1% of the stone's total composition, sneak in.
Just a tiny fraction.
Right. They infiltrate the chrysoberyl crystal lattice. And because these chromium ions have a similar atomic radius to aluminum, they can seamlessly substitute for aluminum ions within that crystal structure.
So you basically have these chromium invaders just sitting in the structural voids where aluminum is supposed to be.
Yes. And the way those surrounding oxygen atoms squeeze and pull on that trapped chromium ion, that dictates exactly how it interacts with light.
Okay, so the structure itself is pressuring the chromium.
Right. It's a phenomenon described by crystal field theory. The specific geometry of that chrysoberyl lattice forces the chromium ion's electrons into a very, very particular energetic state.
And what happens when light hits those stressed out electrons?
When broad spectrum white light hits them, they act as this incredibly aggressive, highly selective filter. They absorb massive amounts of light in the dark blue and yellow regions of the visible spectrum.
Just gobbling it up.
Yeah. Gemological analyses point to a very distinct, intense absorption band centered right at 580 nanometers.
So if we picture the visible spectrum as just this continuous rainbow, the chromium is completely consuming the dark blue and just devouring the yellow.
Exactly. And because it is eating those specific wavelengths, it creates two distinct transmission windows.
Like gaps where the light can actually get through.
Right. It leaves two clear pathways for light to travel through the stone and reach our eyes. There's one window for green-blue light and one window for red light.
Wait, so both green and red light are continually passing through the crystal at the same time?
Always.
Okay, I'm picturing the chromium as like a very strict bouncer at a nightclub.
Ah, I like that.
Right. So white light approaches the door and the chromium bouncer just absolutely refuses entry to yellow and dark blue light. They are rejected, absorbed.
Right, they aren't getting in.
But the bouncer has two VIP lists running simultaneously, one for green light and one for red light.
Yeah.
And whichever VIP group shows up in a larger bus, which is the light source, takes over the club. So if you are standing in the sunlight, the green light arrives in massive numbers, overpowers the red, and the stone looks green.
That is a perfect way to visualize it. And then you walk into a candlelit room. The red light arrives in overwhelming numbers, dominates that transmission window, and the stone appears red.
The bouncer just lets whoever is loudest take over?
Basically, yeah. The chromium is poised precisely at this delicate chemical equilibrium where it transmits both ends of the spectrum equally. The light source is simply tipping the scale.
That is so cool. And there's actually a secondary optical reaction happening with that chromium too, isn't there? The sources noted a pretty dramatic effect when the stone is exposed to ultraviolet light.
Oh, yes. The fluorescence. When you subject natural Alexandrite to long-wave ultraviolet radiation, like a blacklight, those same chromium electrons absorb the high-energy UV photons.
And they get sort of hyperactive.
Yeah, they become wildly excited and actually jump to higher energy orbitals. But that state is unstable, so they almost immediately drop back down to their ground state.
And what happens when they drop?
As they fall, they release that absorbed energy in the form of visible light, causing the gemstone to exhibit this intense glowing red fluorescence.
Wow, a literal red glow in the dark under a UV lamp. That's amazing. But I do want to make sure we're clear on something, because the sources draw a very hard line here.
Right, between the Alexandrite effect and pleochroism.
Yes, because they're not the same thing, but they get confused a lot.
Blurring the two is probably the most common misconception. The Alexandrite effect is driven entirely by the illumination source, sunlight versus incandescent.
Right.
Pleochroism, on the other hand, is a directional property of the crystal itself. It's an optical effect where a gemstone displays completely different colors depending on the physical angle from which you view it.
Regardless of the light bulb.
Right. The light source stays constant. You are just physically turning the stone in your hand and the color shifts.
And Alexandrite is heavily pleochroic, isn't it?
It is intensely pleochroic. Specifically, it is trichroic.
Meaning 3 colors.
Yes. Light travels through the crystal lattice at different speeds along its 3 crystallographic axes, which gemologists label A, B, and C. Because the light is absorbed differently along each of those axes, the stone literally projects 3 distinct colors.
So if you look down one axis,
It appears green. Rotate the crystal to view down the second axis. It appears orange or yellow. Rotate it again to the third axis, and it appears purple-red.
Okay, so just to recap, you have a stone that is changing color from green to red based on the light bulb in the room, while simultaneously projecting 3 different colors, green, orange, and purple-red, depending on the angle you're looking at it. I mean, that presents an absolute nightmare scenario for a gem cutter.
Oh, it is a lapidary nightmare. The cutting process for Alexandrite is incredibly fraught.
I can imagine. What are they even prioritizing?
Well, the cutter's primary objective is to maximize the light source color change. You want that crisp green to red shift to shine straight up through the top facet of the stone, which is known as the table or the crown.
But because of the trichroism, the directional colors, if they mess up the angle.
If they orient the rough crystal even slightly incorrectly on the cutting wheel, those secondary orange and purple colors will bleed into the face-up view of the gem.
Oh man, so it ruins the illusion.
Completely. That bleeding effect, muddying the primary colors, is exactly what ruins the value of poorly cut stones. Instead of a sharp, vivid green shifting to a pure ruby red, you end up with a stone that just looks brownish or grayish or perpetually confused.
A perpetually confused gemstone. That sounds expensive to fix.
It is. A master cutter must analyze the rough crystal, identify those invisible optical axes, and carefully orient the facets to basically trap the pleochroic colors in the sides of the stone while driving that pure color change up through the center.
Which means they probably have to grind away a lot of the stone just to get that perfect angle.
Oh, achieving that orientation often requires sacrificing a massive percentage of the original rough material's weight.
And sacrificing weight in a stone this rare has got to be an agonizing economic decision.
Truly agonizing. Every carat is worth a fortune.
And that rarity is not an exaggeration. The sources get into the geology, and they describe the conditions required to get chromium into a chrysoberyl crystal as a forbidden marriage.
That's the perfect term for it. It is a true geological paradox.
Break that down for us. Why is it forbidden?
Because beryllium, which is the foundational element of chrysoberyl and chromium, the color-changing impurity, do not naturally coexist in the Earth's crust. They belong to completely separate geological regimes.
Like they live in different neighborhoods.
Entirely different continents, geologically speaking. Beryllium is what we call an incompatible light element. During the cooling of magma, beryllium does not easily fit into standard rock-forming minerals.
So where does it go?
It gets concentrated in the residual late-stage magmatic fluids, basically the leftover juices of the magma. and it eventually crystallizes in these coarse-grained igneous rocks known as pegmatites.
Okay, so beryllium is up in these pegmatites. What about chromium?
Chromium is a highly compatible, heavy transition metal. It crystallizes very early in the magma cooling process and remains trapped deep, deep within the Earth's mantle in dense ultramafic rocks.
Like peridotite.
Right, peridotite or dunite. So under normal tectonic conditions, a beryllium-rich pegmatite fluid and a chromium-rich ultramafic rock will literally never intersect.
So how on earth do they ever meet to make Alexandrite?
Creating Alexandrite requires a chaotic, highly localized tectonic event. You need a scenario where a superheated, highly pressurized pegmatite fluid violently intrudes directly into a chromium-bearing ultramafic host rock.
Just smashes right into it.
Yes, this creates a metasomatic contact zone. It's an area of extreme chemical exchange where these two completely incompatible environments bleed into one another. And only in that specific, narrow, superheated crucible can beryllium and chromium actually bond to form color-changing chrysoberyl.
A geological freak accident.
Precisely.
And that accident occurred in a very specific location to give us the first documented Alexandrites. Which brings us to the history. Because the story of its discovery in the 1830s reads less like a geological survey and way more like a geopolitical thriller.
Oh, it really does.
Yeah.
Set deep in the Ural Mountains of Imperial Russia near the Tokovaya River.
Right. And the miners there, they weren't even looking for chrysoberyl.
No, they were operating in these mica schist veins.
Yeah.
The local miners referred to those formations as glimmerites because the rich mica content literally made the rocks shine and reflect light in the sun.
And what was their primary target?
Emeralds. When they unearthed these hard green crystals, the immediate assumption was simply that they had found a particularly durable, clean variety of emeralds.
Which makes sense. They look green in the daylight. But then, and this is my favorite part of the story, the miners take the day's yield back to the camp. The sun goes down. They light the lanterns and candles to inspect the haul. And suddenly,
the emeralds they dug up that afternoon are glowing a vibrant raspberry red.
can you imagine? You'd think you were losing your mind.
It would be terrifying. And the shock of that visual transition quickly moved the stone up the chain of command right into the highest echelons of the Russian aristocracy.
And they named it in honor of the future Tsar, Alexander II.
Yes. The timing was highly fortuitous. The discovery coincided perfectly with his coming of age, his 16th birthday, which was when he officially stepped into his role as heir apparent.
But beyond the timing, the optics were just a political masterpiece.
Oh, completely.
Because the vibrant green and the deep red of the stone, those perfectly mirrored the official colors of the Imperial Russian military forces.
It couldn't have been scripted better. The gemstone essentially acted as a piece of geological propaganda,
Like a nationalistic symbol baked into the earth itself.
validating the Romanov dynasty. It was rapidly embraced by the nobility and integrated into the high jewelry of the era by houses like Fabergé.
But here's where it gets really interesting. The official historical record of who actually discovered and identified the mineral, it is highly contested.
It's a huge point of debate. The narrative that's most widely accepted in Western gemological literature credits a Finnish mineralogist, Nils Gustav Nordenskjöld.
Right, and according to this version, Nordenskjöld received a specimen from a really powerful Russian official, Count Lev Alexeyevich Perovsky.
Correct. And Nordenskjöld tests the stone's hardness, finds it to be significantly harder than an emerald, observes the color change under candlelight, and correctly identifies it as a novel, chromium-bearing variety of chrysoberyl.
And Nordenskjöld actually intended to name it something totally different, right? Diaphanite.
Diaphanite, yes. But Count Perovsky, recognizing the immense political capital that the stone represented, basically preempted the mineralogist and christened it Alexandrite to curry favor with the imperial family.
Classic political maneuvering. But then there's this competing historical narrative championed by Russian historians.
Yes, and this one centers on the actual manager of the Ural mines, Yakov Kokovin.
Kokovin.
Right. Kokovin was a highly skilled lapidary and the director of the Ekaterinburg lapidary works. This alternate history argues that Kokovin was actually the first to truly recognize and isolate the stone's unique properties right there on site.
But the Kokovin narrative takes a very, very dark turn.
It's incredibly tragic.
Because Count Perovsky, the same guy who named the stone, eventually accuses Kokovin of embezzling royal jewels and mismanaging the imperial yields.
Yes.
Yeah.
And Kokovin is summarily stripped of his titles. He's arrested, and he dies in prison under very mysterious circumstances.
Often cited as suicide, but, you know.
Very convenient for Perovsky. By removing Kokovin, Perovsky completely consolidated his control over the Ural mines' output and cemented his own legacy in the gemstones' naming rights.
It is just a stark example of how the lore, the value, and the very history of a mineral can be manipulated by sociopolitical power structures.
Absolutely.
And that geopolitical history is not just fun trivia. It directly impacts the modern economic reality of the gemstone. The narrative of the Russian czars is factored heavily into the price per carat today.
Oh, massively.
Yeah.
Mostly because the original source material is virtually extinct.
The Russian mines are empty?
Pretty much. The legendary Russian mines, like the Mariinskoye deposit, were systematically exhausted of fine, gem-quality material by the late 19th and early 20th centuries.
Wow, so they mined it out fast.
They did. While there have been sporadic small-scale recovery efforts over the years, commercial production largely collapsed with the fall of the Soviet Union. Fine Russian Alexandrite is astonishingly rare on the modern market.
So if you actually have one,
A verified Russian origin commands an astronomical financial premium over stones mined literally anywhere else in the world.
so for decades, the global supply of new Alexandrite was just a trickle.
Barely that.
But that changed abruptly, right, in 1987.
Yes, with a massive geological strike in Brazil, specifically in the state of Minas Gerais at the Hematita mine.
And the Hematita discovery basically fundamentally altered the market.
It completely revived it. The geological conditions in that specific Brazilian pegmatite district produced crystals that rivaled, and in some metrics, honestly exceeded the quality of the original Russian material.
Really? The sources describe the Brazilian stones as having spectacular optical shifts.
Oh, they are phenomenal. They exhibit a highly saturated bluish-green to teal color in natural daylight, and they transition to a very intense, vivid red-purple under incandescent light.
So the color change is really crisp.
Extremely crisp and dramatic, which immediately positioned Brazil as the new premier source for high-quality Alexandrite.
But Brazil isn't the only modern source. Beyond Brazil, the gem gravels of Sri Lanka, historically known as Ceylon, represent the other major global source.
Yes, Sri Lanka is a major player, but the Sri Lankan deposits yield a very different profile of gemstone.
How so?
Well, Sri Lanka is famous for its secondary alluvial deposits.
Yeah.
So millions of years of weathering and water transport have concentrated these heavy, durable minerals in gravel beds.
Right, like tanning for gold.
Exactly. Because of the specific geochemistry of that region, Sri Lankan Alexandrites grow to much larger sizes, and they often boast vastly superior internal clarity compared to their Russian or Brazilian counterparts.
So you can get bigger, cleaner stones.
It is entirely possible to find massive, virtually flawless crystals from Sri Lanka.
There's got to be a trade-off, though.
There is. The trade-off is in the color chemistry. The color shift in Sri Lankan stones is generally much weaker and more muted.
Why is that?
It's the presence of other trace elements. Things like iron can interfere with that pure chromium color change. So instead of jumping from emerald to ruby, a Sri Lankan stone might display like a yellowish green or olive color in daylight and then shift to a brownish red or a purplish brown indoors.
Ah, so it's a bit muddier.
Right, the stark, vivid contrast is often missing. There are also smaller, commercially viable deposits in Tanzania, Madagascar, and India, but the market largely views Russia and Brazil as the standard bearers for color saturation.
And Sri Lanka as the source for size and clarity.
Precise.
Okay, so if the original Russian stones are virtually extinct, and a Brazilian stone of identical size and color will sell for a fraction of the price of a Russian stone.
You see where this is going.
The financial incentive to lie about a gemstone's origin is astronomical. We are talking about tens of thousands of dollars in value, hinging entirely on where the rock was dug out of the ground.
Exactly. Which means the naked eye and even a highly trained jeweler's loop are no longer sufficient. We have to rely on atomic-level verification to catch modern fraud.
Right. And this is where the rigorous protocols of institutions like the GIA become absolutely vital.
Essential. When a high-value Alexandrite enters a modern gemological laboratory, it is subjected to a battery of highly advanced spectroscopic and chemical analyses.
It sounds like a CSI lab for rocks.
It really is. The primary objective is just establishing basic authenticity. Like, is the stone natural, synthetic, or a complete imitation?
And the frontline defense for that question is a technology called FTIR.
Yes. Fourier transform infrared spectroscopy.
Okay, break that down for us.
It relies on the principle that molecular bonds vibrate at very specific frequencies. So, the lab directs an infrared beam straight through the gemstone.
Okay.
As that invisible infrared light passes through the crystal, the chemical bonds within the stone absorb specific wavelengths of that energy to basically fuel their vibrations.
So the stone is literally vibrating.
At a molecular level, yes.
Yeah.
And the spectrometer measures exactly which infrared frequencies are absorbed and which pass through, creating this unique absorption spectrum graph.
So it's looking for the signature of how the stone was born.
Exactly. Natural stones grown over millions of years in the Earth's crust trap different microscopic impurities like specific water molecules or mineral traces than a synthetic stone that was grown rapidly in a laboratory crucible using chemical fluxes.
So FTIR can almost instantaneously identify those distinct vibrational signatures.
Definitively proving whether the crystal is natural or laboratory grown.
But FTIR cannot tell you where a natural stone was mined, right?
No, it can't map the geography. To prove a stone is from the Urals and not Minas Gerais, the labs utilize LAICP-MS.
LAICP-MS, laser ablation inductively coupled plasma mass spectrometry. That is a mouthful.
It is arguably the most powerful tool in modern gemology.
Okay, walk us through how this laser works, because the sources described this and it sounded crazy.
It is pretty intense. The process requires removing a microscopic, invisible amount of material from the gemstone. Usually they target the girdle, which is the thin outer edge of the stone.
Right.
They fire an incredibly precise B.O.O.G laser at the stone, which ablates or vaporizes a crater just a few microns across.
So they are essentially blowing up a few nanograms of a $50,000 gemstone?
Basically, yes. It is technically a destructive test.
That sounds terrifying.
But it's on a scale so small it absolutely does not impact the gem's weight or its visual integrity.
Okay, phew. So they zap it with the laser, then what?
That vaporized plume of gemstone material is captured in a carrier gas, usually helium, and it gets swept into an inductively coupled plasma torch.
A plasma torch.
Yes, this argon plasma operates at temperatures approaching 10,000 Kelvin.
Wait, 10,000 Kelvin? Isn't that hotter than the surface of the sun?
It is hotter than the surface of the sun. The intense heat completely atomizes the gemstone vapor. It tears the molecules apart and strips the electrons away to create charged ions.
Okay, so the gem is just completely disintegrated into ions.
Right. Those charged ions are then fired into the mass spectrometer, which uses an intense magnetic field to bend their flight path.
Bending their path. Why?
Because lighter ions bend sharply, while heavier ions have more momentum and take a much wider curve. By measuring exactly where those ions land on the detector, the machine calculates their exact mass-to-charge ratio.
Wow, so it sorts them by weight.
Exactly. This allows the lab to catalog the exact chemical inventory of the stone down to parts per billion.
Parts per billion, that is unfathomably precise.
It has to be, because they are not looking for the beryllium, aluminum, or chromium. They already know those are there. They are looking for the trace elements.
Yeah, accidental impurities.
Right, the accidental impurities that were present in the local soil when that specific crystal formed. They look for specific ratios of magnesium, iron, gallium, germanium, tin, and boron.
And those trace elements act as a geographical barcode, because the crustal chemistry of the Ural Mountains is fundamentally different from the gem gravels of Sri Lanka.
Exactly. Sri Lankan stones, for instance, consistently demonstrate elevated levels of boron. They typically register greater than 20 parts per million by weight. Indian and Tanzanian stones frequently present high concentrations of magnesium.
And what about Russia? How do you verify a Russian origin?
Russian stones are chemically distinguished by significantly high levels of germanium. By plotting the concentrations of all these trace elements against a known database, gemologists can pinpoint the stone's geological birthplace with incredible statistical confidence.
That is just, it's amazing. Chemistry provides the barcode, but the labs also rely on visual forensics, don't they?
Yes, the microscope is still essential. The internal microscopic landscape of a gemstone, the inclusions, provides a powerful secondary geographic signature.
Because as a crystal grows over millennia, it just engulfs microscopic bits of its surrounding environment.
Exactly. These trapped minerals, fluids, and growth structures are highly diagnostic.
Right.
For example, if a gemologist looks through a microscope and observes tiny, opaque, metallic-looking sulfide crystals trapped within the Alexandrite,
What does that mean?
that is a massive indicator of Brazilian origin. It's directly related to the geochemistry of that hematite deposit.
Okay, so sulfide crystals mean Brazil. What about Russia?
If the microscope reveals long, prismatic, rod-like crystals of the mineral tourmaline or intricate cotton-like clouds of tiny particles, Those specific internal features point very strongly to a Russian origin.
And Sri Lanka.
Sri Lankan stones, while generally much cleaner internally, often exhibit strong brown color zoning.
Color zoning.
Yeah, distinct straight bands of concentrated brown color that are just visibly striped within the crystal structure. So combining the chemical data from the mass spectrometer with the visual evidence of the inclusions gives the lab a definitive, rock-solid answer.
Which is absolutely essential, because the retail marketplace is completely saturated with material designed to deceive the buyer.
Oh, it's a minefield out there.
The sources detail a whole hierarchy of fakes and simulants that really require vigilance.
Right. At the bottom end of the market, you find cheap simulants like standard glass or synthetic color change spinel.
And those are pretty easy to spot, right?
Usually, yes. These materials might mimic a vague, muddy color shift, but they completely lack the hardness, the high refractive index, and the crisp optical performance of real chrysoberyl.
But there's a far more deceptive simulant, isn't there? The color change sapphire?
Ah, yes. This one accounts for a massive percentage of vintage jewelry sold under the name Alexandrite, especially jewelry from the mid-20th century.
So what is it, actually?
It is synthetic corundum, laboratory-grown sapphire that has been chemically doped with the trace element vanadium during the growth process.
Vanadium, not chromium.
Exactly. The vanadium forces the sapphire to exhibit a color change, typically shifting from a grayish blue in daylight to a purplish pink indoors.
So it does change color, but it completely lacks the lush, vibrant emerald green daylight color that defines true Alexandrite.
Right. And structurally, it is just a sapphire. It's not chrysoberyl.
But the most complex category has to be the laboratory-grown Alexandrite.
Without a doubt, this material is not a fake in the chemical sense. It is real chrysoberyl, doped with real chromium.
So it's literally the exact same thing.
Chemically, yes. It possesses the identical chemical formula, the exact same 8.5 hardness on the Mohs scale, the same refractive index, and often an utterly spectacular, completely flawless color change.
How do they even make it?
The sources outline two primary methods for growing it. First is the Czochralski-Pulled method.
Czochralski.
Right, where a seed crystal is slowly, carefully drawn upward from a crucible of molten beryllium aluminum chromium soup.
Sounds delicious.
Yeah, very toxic, actually. And the second is the flux melt method, which dissolves the chemical components in a molten flux and allows them to crystallize slowly over several months.
So it's chemically identical. How can the labs even tell them apart?
Because they are grown in controlled environments, they leave clues. Labs can definitely identify them. Czochralski stones often display curved growth stria.
Like tiny curved lines.
Exactly, microscopic arcsing lines that portray the spinning motion of the pulling process. Or they might have tiny, perfectly spherical gas bubbles which do not occur in natural chrysoberyl.
What about the flux-grown ones?
Flux-grown stones often contain highly reflective metallic inclusions of the flux material itself, like bits of platinum or molybdenum from the actual crucible they were grown in.
Okay, I have to play devil's advocate here for a second.
Go for it.
Because I think a lot of listeners are wondering this. Imagine you were looking at two rings. Ring A holds a natural Russian Alexandrite. It has some visible internal inclusions. The color changes, let's say, 80% saturated, and it commands a price of $50,000 per carat.
A very realistic scenario.
Okay, now Ring B holds a Czochralski lab-grown Alexandrite. It is chemically identical, structurally identical, internally flawless, exhibits a vivid 100% green to red shift, and costs a few $100s. If the synthetic stone is physically perfect and vastly cheaper, why on earth does the market support a $50,000 valuation for the natural stone? Is it just geological snobbery?
That is the ultimate question. But it addresses the core philosophy of gemological valuation. In the realm of high-end gemstones, value is not derived solely from aesthetic perfection.
What is it derived from?
Value is driven intrinsically by extreme rarity and the provenance of natural history.
It is the ultimate expression of supply and demand, isn't it?
Precisely. We have the industrial capacity to manufacture millions of carats of flawless lab-grown Alexandrite every single year. The supply is functionally infinite, which inherently caps its financial investment value.
Right. Anyone can buy one anytime.
But the Earth will never, ever produce another 19th century Russian Alexandrite from the Ural Mountains. The geological conditions that created them are gone, and the mines are empty. That supply is rigidly finite.
So you're buying history.
When a collector purchases a natural Alexandrite, they're not just buying a pretty optical effect. They're acquiring a tangible piece of the Earth's deep tectonic history, a survivor of an incredibly rare geological collision.
So, lab-created stones offer an accessible, beautiful way to enjoy the optics of chromium on a daily basis. But they lack the millions of years of geological storytelling and the absolute scarcity that drives the high-stakes auction market.
It ultimately depends on the buyer's objective,
Okay.
right? Are you purchasing an accessible piece of optical physics, or are you investing in a finite geological artifact?
That makes total sense. But regardless of whether you are wearing a historic Russian heirloom or a modern laboratory creation, the physical structure of the crucible crystal offers a massive practical advantage,
Oh, yes. Supreme durability.
which is huge. If you are going to invest in a gemstone, especially for a ring you wear on your hand, you need to know how it behaves in the physical world.
Durability is a triad in gemology. It's composed of hardness, toughness, and stability. And Alexandrite excels in all three.
Let's start with hardness.
Okay, on the Mohs hardness scale, which measures a mineral's resistance to scratching Alexandrite, ranks at an 8.5.
And for context, a diamond defines the absolute top of the scale at a 10.
Right. At 8.5, Alexandrite is exceptionally resistant to abrasion. It is significantly harder than standard silicate minerals like quartz or feldspar, which actually make up the bulk of everyday dust and dirt.
So we'll get scratched up by just existing in the world.
Exactly. It is harder than emeralds, which sit between 7.5 and 8, and harder than garnets, spinels, and tourmalines. Within the entire spectrum of recognized gemstones, chrysoberyl is surpassed in hardness only by corundum, which is sapphires and rubies, at a 9, and diamonds.
So it will easily resist the microscopic scratches that dull softer stones over time. But hardness is only one metric, right? Because an emerald is technically hard, but it is notoriously brittle.
Oh, highly brittle.
Yeah.
If you strike an emerald against a granite countertop, it is very prone to shattering.
Right. So where does Alexandrite sit on that front?
This is where Alexandrite's structural toughness becomes critical. The sources highlight a specific mechanical property. Alexandrite lacks distinct cleavage.
Okay, cleavage is a term that definitely needs untangling for anyone outside of a geology lab.
Fair enough. The easiest analogy is the grain in a piece of wood.
Okay.
If you swing an axe and strike the wood parallel to the grain, the structural bonds give way effortlessly, and the wood splits cleanly in two.
Right. It just pops open.
Many crystalline minerals possess a similar internal grain. Diamonds and topaz, for instance, have distinct cleavage planes. These are flat internal directions where the atomic bonds holding the crystal together are significantly weaker.
So if you hit it wrong.
If you apply sudden pressure or physical shock at the precise angle of that cleavage plane, the gemstone can just split or shear apart completely.
Wow. But the chrysoberyl lattice doesn't have those.
It does not. It does not possess a uniform internal grain. If an alexandrite is subjected to blunt force, it does not split along flat planes. Instead, it breaks with what we call a conchoidal fracture.
Conchoidal, like a shell.
Exactly. Similar to how a thick piece of glass chips in a curved shell-like pattern. Because it lacks cleavage, it is incredibly tenacious. It is highly resistant to the chipping, fracturing, and structural failure that constantly plague stones like emeralds during normal wear.
So what does this all mean for the person wearing it? The practical application of that toughness is massive. It means you can wear a phenomenally complex, color-changing gemstone on your hand without treating it like a fragile museum piece.
Exactly. You don't have to baby it.
Right. It does not require the hypervigilant care of a pearl or an opal or a heavily included emerald. It is structurally engineered to actually survive the impacts of daily life.
And that combination of optical uniqueness and mechanical toughness has driven a massive surge in Alexandrite's popularity, specifically as an alternative engagement ringstone.
Oh, that makes a lot of sense.
Yeah, consumers are actively seeking stones outside the traditional diamond paradigm, but they still require a mineral capable of withstanding, decades of daily physical exposure.
It also holds a pretty prominent position on the modern birthstone calendar.
It does. In 1952, the jewelry industry officially added Alexandrite as a birthstone for the month of June, sharing the designation with the pearl and the moonstone.
If we connect this to the bigger picture, though, from a symbolic perspective, the intersection of its physical durability and its optical mutability is pretty profound.
It really is. It is a stone defined by its ability to completely transform its appearance based on shifting external environments, while its internal physical structure remains incredibly rigid and unyielding.
Adapting visually to new light, but structurally refusing to break.
Beautifully said. which perfectly explains its designation as the traditional gemstone for the 55th wedding anniversary.
Of course. Surviving 55 years requires an immense capacity for both endurance and transformation.
Absolutely. Though even with its supreme toughness, the jeweler's guides provided in the sources do outline baseline care protocols. It is tough, but is not invincible.
Right. What should people avoid?
It should be protected from extreme sudden temperature changes, like the intense heat of a jeweler's torch during repairs, though normal environmental heat is completely fine.
Like leaving it in a hot car is fine.
Yeah, that's fine. It should also be kept away from harsh, corrosive household chemicals, like hydrofluoric acid.
What's the best way to clean it then?
The recommended cleaning protocol is entirely straightforward. Warm water, mild soap, and a soft bristled brush to gently remove oils and debris from behind the facets.
Super simple.
Very simple. While its toughness generally allows for ultrasonic or steam cleaning, manual cleaning is always the safest baseline for high-value colored stones. Treat the crystal with basic respect, and its physical integrity will easily outlast the wearer.
Wow. This journey through the data reveals a stone of absolute extremes.
It really does.
We started deep within the Earth's mantle, examining the chaotic tectonic violence required to force totally incompatible elements like beryllium and chromium into a single localized crystal lattice.
We traced its extraction from the glimmerite veins of the 19th century Ural Mountains, where its optical properties were leveraged as literal political propaganda for the Russian Empire.
And followed its geographic expansion to the pegmatites of Brazil and the alluvial gem gravels of Sri Lanka.
We dismantled the physics of the color change, watching the chromium ion act as this selective barrier, absorbing the yellow and blue light and forcing the stone to pivot from green in the sun to red in the firelight.
We saw how modern gemology deploys lasers, argon plasma, and mass spectrometers to read the atomic barcode of its origins, defending the market against an endless tide of synthetic simulants.
The ultimate takeaway is that understanding the cold, hard mechanics of the stone, knowing the exact nanometer absorption bands, the trace element parts per million, the crystal field theory, it does not diminish the aesthetic wonder of the gem. It elevates it.
Completely.
Wearing an Alexandrite means wearing a localized anomaly of optical physics and deep earth geology.
The knowledge proves that the magic isn't a trick. It's just incredibly complex science. But as we synthesize all this data, there is a fascinating environmental shift occurring that directly threatens the entire premise of the Alexandrite legend.
Okay.
We established early on that the dramatic emerald by day, ruby by night contrast relied entirely on the strict binary of 19th century light.
Right. Sunlight versus candle fire.
Exactly. When the miners pulled those first crystals out of the Urals, humanity lived in an environment defined by extreme lighting contrasts. You had the broad spectrum, cool blue-green dominance of natural sunlight during the day, and as soon as the sun set, you transition instantly to the narrow, red-heavy, warm spectrum of a burning candle, a lantern, or a hearth fire.
The transition was sharp, immediate, and absolute.
And that stark environmental dichotomy is what allowed the stone to pull off its famous color shift. But our modern world has fundamentally rewritten that spectrum.
Oh, that's a really good point.
We no longer rely on the sun and fire. We live under a canopy of artificial illumination. We are surrounded by LED screens, compact fluorescent tubes, and customizable smart bulbs. Our offices are flooded with artificial daylight that deliberately mimics the blue spectrum of the sun.
Right. You can literally walk into your living room at midnight and ask a smart speaker to adjust your overhead lights to a cool white or a daylight balance of 5,000 Kelvin.
Exactly. Our artificial lighting environment is no longer restricted to the warm reds of a tungsten bulb or a candle. It is infinitely variable, customizable, and synthesized. We are smoothing out the extreme ends of the spectrum, constantly bathing ourselves in blended neutral light.
We're erasing the contrast.
We are. So the question becomes, as our 21st century environments become endlessly flooded with variable artificial daylight, are we permanently erasing the stark, magical ruby by night experience that defined the stone for the Russian czars? Are we homogenizing the light spectrum so thoroughly that the ultimate chameleon gemstone is slowly losing its ability to shift, effectively trapped in its green state by our own technological progress?
That is a phenomenal question.
It is a striking thought to carry with you the next time you adjust a dimmer switch or buy a smart light bulb. You might expect the red stop sign to remain red, but when it comes to Alexandrite, the only certainty is change. Thank you for joining us on this deep dive into the data. Keep questioning what you see, and we will catch you next time.